Hello, my name is Ramon Sosa. Today, my partner Kyle Edmonds and I will give you a brief survey of the technology that goes into manufacturing an advanced composite oar. Let's start off with the basics. As I'm sure you know, an oar is the simplest propulsion method for moving a boat on the water. Oars have four components: the handle or grip, the shaft, the sleeve, and the blade. We'll be discussing oars specifically used in the competitive sport of rowing, and these can either be short sculling oars used in pairs or long sweep oars, both controlled by a single rower. Oars are used by river sports enthusiasts, club and collegiate rowing teams, and up to the Olympic and world competitive level. In higher applications, any advantage over your competition is key to winning, so these strong and lightweight composite oars replace the wooden oars used since man first took to the seas. These oars are designed to perform under the most rigorous of rowing sprints, when rowers apply almost 900 newtons of force during their sweep, placing the oar shaft under 200 megapascals of stress. Composite oars are also lightweight, weighing at most 5 kilograms, far less than standard wooden oars. They are also much stiffer than wooded oars, reducing energy loss to elastic strain. Teams all over the world rely on these composite oars to take a beating and last for at least 4 years under these high loads and when exposed to lake and seawater, requiring them to be durable and resistant to damage. Depending on the level of competition, the oars are priced between $400 and $1,000. So what are these oars made of that allow them to perform so effectively? The bulk of the shaft and blade are made of carbon and glass fiber reinforced vinyl ester resin matrix. The blades are made of polyurethane foam sandwiched between glass and carbon fiber laminates. The sleeve is made of tough thermoset polyurethane, which protects the shaft from abrasion during sweeps and connects the oar to the oar locks in boat. The handle is made of fine grain wood or rubber, often a preference of the athlete. The oars are designed to maximize performance and minimize weight. The shaft length is tailored to fit athletes of any size, but are typically no more than 30 millimeters in diameter, with the thickness varying depending on manufacturer's technique. Fiber loading of up to 65% can be achieved, and would allow the shaft to be so stiff and strong. To protect the structural components in the shaft and blade, a thin polyurethane coating is applied to waterproof and prevent damage. Additionally, and Kyle will get into this later, the angle at which the fibers are wound also contributes to the stiffness and strength of the final product.
Composite oars are manufactured in 4 separate components that are molded and shaped using different methods. The 4 components are the shaft, the blade, the sleeve, and the handle. The shaft is manufactured using filament winding. To make the shaft, glass and carbon fibers are used in different layers. The first layer contains glass fibers, which are led into a vinyl ester epoxy resin bath. A wiping device ensures that there is approximately 75% fiber and 25% resin. The winding head then wraps the fiber around the mandrel that resembles the shape of the shaft. The second and third layers are wound in the opposite direction as the first and are also made of glass fibers. The fourth and final layer is wound in the same direction as the first, except carbon fibers are used. The second part of the oar is the blade. The blade is manufactured using a hand layup method. Glass and carbon fiber prepregs are placed onto a cold mold with a vinyl ester epoxy resin. The mold is clamped together and a low-density structural foam is added to the inner cavity of the mold. The third component of the oar is the sleeve. The sleeve is simply a polyurethane thermoset that is placed into a mold. The mold clamps down around the shaft and provides an even layer of polyurethane to protect the shaft from water intrusion and abrasion from the environment. Once all the components are manufactured and cured, they are glued together using a polyurethane glue. A clear urethane finish is applied to the surface of the oar to further protect it from the environment. Once the oar is completely finished, it must undergo a stiffness test to ensure that the oar meets performance requirements. A 10-kilogram weight is placed at the end of the shaft where the blade is attached, and the other end is fixed. The displacement is measured to ensure that the stiffness is in the correct range. The acceptable deflection range is 55 to 65 millimeters, but this range can vary depending on the customer's needs. The oar is visually inspected for any other damage during the test, and the process is complete. Here is a table of the materials and labor costs. These prices are estimates based on generic products, so these costs may vary widely. The cost analysis doesn't include any machinery because the variation from company to company would be too high. The typical price for an oar ranges from $400 to $1,000, depending on the end user.